All right. So, lovely to see you all. Welcome to Lecture 11, where we're talking about first-order natural deduction. So, what we're really going to be doing is kind of extending the stuff that we've been talking about for the last 2 weeks, right? This natural deduction system where we've been using it and applying it to truth functional logic. And we're going to use it and apply it now to first-order logic. So what I'd like to do is I want to walk you through all of the new rules we're going to get. And it's worth just saying right off the bat, there's not really that many new ones. In fact, I think there's going to be 8 basically that we'll get. They're actually pretty easy and pretty clear, but the core to almost all of them is going to be a concept that can sometimes be hard to get our heads around, which is the idea of an arbitrary name. So we're going to try and go through these slowly together to make sure we have a grip on the rules. Then after we've talked through the new natural deduction rules, we'll talk about proof-theoretic concepts for first-order logic. Shock horror, this is going to be almost exactly the same as what we did with TFL. Like, it's even the same slides, I've just changed 1 or 2 words. Because the concepts are the same, it's just the system applied to that language instead of TFL. And lastly, the kind of big take-home and the big reason why we wanted to do natural deduction is I, again, want to talk to you about the relationship between our proof-theoretic concepts, the stuff that we can define in terms of the single turnstile, and our semantic concepts, the one we defined in terms of interpretations and the double turnstile. So that's the plan, and we'll just sort of work through it and see how it goes. So let's start by talking about this FOL natural deduction rules. And again, what we're really going to do here, I'm going to lay out the rules for this natural deduction system. I'm going to talk through all of them just to kind of show you what all of the moves are going to be like. So, to start, the big thing, the nice thing, is our FOL natural deduction system includes everything from TFL. So all of the moves and rules that you already know how to make or use, they work here too. So everything that we've learned continues on. We can still use all the tricks and all of the stuff that we've learned. But we're going to get a few more rules. Specifically what we're going to have introduction and elimination rules for both quantifiers. So universal introduction, elimination, existential introduction and elimination. We're going to have what we'll call quantifier conversion rules. These are ones that basically let us play swapsies. If you have a quantifier next to a negation, you can swap them around. And the last kind of pair of rules, interesting ones, are about identity introduction and identity elimination. So we'll go through these one by one. And just to say, some of them are really easy. For example, universal elimination, very, very easy. Existential introduction, very, very easy. In fact, the easiest rule we'll have is going to be identity introduction. It's the only rule that doesn't need to cite another line. It literally lets you bootstrap a sentence from nothing at all. The other ones, though, are a little bit more complicated. So we'll talk through them. And we'll go through them in order. So we can start with universal elimination. Universal elimination is a very simple, straightforward rule. It says, roughly, from the claim that everything is F, you can derive some particular thing is F. That is, if you have a sentence that's got a universal quantifier as its main operator, you can replace the associated variable with any name you want. Any name, no restrictions. It can be a name that's already in the sentence. It can be a totally new name, whatever you want. The only restriction here is that you need to replace every associated variable. So if, for example, the sentence was universal x, fx conjunction gx, right, you need to plug in the same name for both x's. So our first rule, the first new rule, pretty straightforward. If you've got a universal, you can replace the associated variable with any name you want. And again, hopefully the idea there makes sense, right? If it's a universal, it works for everybody, so you can use any name. So universal elimination, fairly straightforward. The flip side, unfortunately, not so much. Universal introduction. How do we get a sentence featuring a universal as its main operator? So here's a thought, a naive thought. If we could show that every possible use of a name for sort of f blank would give us a true sentence, right, then we of course could infer universal quantifier. But the problem is there's no way to do this. This is a super task because there's an infinite, accountably infinite number of potential names we can plug in. So there's no way we could ever test that. So a very naive thought of just, oh, if every single name plugged in gives you this, you could introduce the universal. Well, that's not going to work. And note, we can't kind of manipulate things by restricting a domain like we might do when we're building interpretations, because that requires us thinking about the truth or falsity of these sentences. We're just thinking purely syntactically. So we can't do it with just names. So what the hell do we do? Well, here's what we do. If we can show that our sentence, right, the f blank, holds when we plug in what we'll call an arbitrary name, then we'll know that the universal quantification is true. And the arbitrary name is, much as the name of this thing suggests, haha, right? It's a name that kind of just stands for no one and everyone. We dealt with this once before. If you remember, when we were thinking about interpretations, and we had the idea, there was a question about like, hey, for everything in the domain, there's something that's older than it. Way back, I know that was like lecture 6, so it was a while ago. But we talked about that case, and remember our domain was the Simpsons characters. And we said, look, we don't know who the oldest one is. Could be Mr. Burns, it could be somebody else. But whoever the oldest one is will be our counterexample. That was an instance where we had effectively an arbitrary name. We didn't know who the name was for, but we could kind of plug a blank name in. So the key name is arbitrary names are almost, if you like, grammatical placeholders. They're names, but who are they names for? Now, before we go on, does the idea of arbitrary name make sense? Be honest. Yeah, okay, nice. Couple hands. Please.
The same thing or?
Kind of. So importantly, we're going to have some restrictions to ensure that the name is arbitrary. What we really mean by this is it can't be a name that actually picks something in the domain out. It needs to be, if you like, a dummy. So an easy example. We'll come to it in a minute. But an easy example, we can see the rule. If what we can plug in here is some name, let's say Steve. Who's Steve? Don't know, don't care. Steve just is a name, it's functioning as a name. What does it pick out? We do not care. But if we know that it functions as a name, and we know that this name Steve makes the sentence true, then it doesn't matter that we've used Steve. So for example, right, if we have the domain of people in the room, and we say, Steve's in the room. Right? True. Why is it true? Because of the way we set the domain up. Doesn't matter who Steve picks out. It works as an arbitrary instance. That's the kind of rough and ready idea. We'll come back to Steve a few times. So, syntactically, how do we actually restrict the rule? We'll say if you have a sentence that looks like this, with some name, C, in it, right? And C does not appear in any undischarged assumption. So what does that really mean? it means it's not in your opening assumptions, and if you're in the subproof, it's not in the sentence you opened your subproof with. So it's not in any undischarged assumptions, and the variable we want to plug in isn't already in the sentence. That's just to avoid clashes of variables. Then we can replace C with a universally quantified variable. Notably, the other restriction is that every occurrence of C has to be replaced. So again, the intuitive thought here is kind of weird, but roughly is if we can fill in some name, and it doesn't matter who the name stands for, but that name still makes the sentence true, then it will be true for everyone. Again, you can kind of think about it as, let's plug in some name and have it just stand in for general person in the class. Okay, we'll call him Steve. What's Steve like? Well, don't really know a hell of a lot about them, but we know that they're in the class. So then that would let us go to the universal quantified sentence. Everything in the domain is in the class. Again, it's a cheap example, but it gives us an idea. The things to remember are this. Whatever name that we're treating as arbitrary just cannot appear in any undischarged assumption. So what that really means is not in your opening assumptions, the stuff above the assumption line, or if you're in a subproof, the additional assumption that opened the subproof. Again, kind of intuitive, because these are the things that count as our assumptions. If we're in the subproof, the thing we started with is undischarged until we close it and move away. So there's our first kind of pairing. To go back a slide or two, universal elimination. If you've got a sentence featuring a universal, cool, plug in whatever name you want, go nuts. Universal introduction, you can replace the name with a universally quantified variable, provided the name is arbitrary, and provided you replace every single instance of the name. Okay. So those are our first two new rules. One of them very straightforward, one of them less so straightforward. So let's move to the existential. The existential has one easy one and one tough one. The easy one is existential introduction. The idea here is that from the claim that some particular thing is F, you can conclude something is F. Right? If you know that Steve is in the room, then you know someone's in the room. So, in terms of the rules, if we have a sentence featuring a name, you can replace the name with an existentially quantified variable. The only restriction here is that whatever variable you want to use can't already be in your sentence. And that's just so you don't end up with a clash of variables. Remember before when we couldn't have the X associated with two different quantifiers? It's the same idea. The really neat thing about existential introduction is that you're not restricted to replace every occurrence. You can replace some or all. So if you have a relational claim, like say TCC, from this you can get three different sentences using the same rule. You can either get the existential introduction where we just replace the first instance, or the second instance, or both. Three different existential sentences, all from using that same one rule. But again, the general thought here is fairly straightforward. If you know that a particular thing satisfies the sentence, you know something in the domain does. Makes sense. So existential introduction, down the line, fairly straightforward. Existential elimination, not so much. Unfortunately. So to get a run-up to existential elimination, the first thing to note is that existentials are very much like disjunctions. In that, hey, they're really easy to introduce, they're very hard to eliminate. They're easy to make true, you just need one thing in the domain. They're very hard to know what you can derive from. because you need to know, well, which thing in the domain. So we're not going to really be able to get particular names out, but we can use the same trick we did before with arbitrary names. So here's the idea for existential elimination. What we're going to do is replace the existentially bound variable with an arbitrary name. And if whatever we get kind of comes out from that, following from the arbitrary name, we'll know that it follows from the existential. Let me give you an example and it'll be a little bit clearer. So suppose we know that something's F, but we don't know what thing, and that everything that's F is also G. So we know somebody's F, and we know everything that isn't F is also a G. Again, we don't really care what those properties are, we're just thinking about those sentences for a second. Since something is F, we know that at least some particular thing, maybe a bunch, but at least one. Problem is we don't know much about it. We don't know who it is, which object from the domain it is. Cool. Let's just call it Steve. Who's Steve? Don't know, don't care. We know he's in the domain, and based on the very first sentence, the only thing we really know about him is that he's an F. Steve is just a name that we picked out of the ether to let us talk about the thing that is F. And notably, even calling it the thing is kind of a mistake, because Steve might in fact be referring to a bunch of different objects. So we don't know much about Steve, but we know by stipulation Steve is F. Because who is he? Well, he's just an arbitrary name that we picked out to name whatever happens to be F, the thing that is F, right? Because again, we know something's F. Then, since we've stipulated that Steve is F, and we're told everything that's F is G, then we can conclude since Steve is an F, he must also be a G. And finally, we can discard our commitment to using the name Steve and just say, okay, look, everything we've done, we use that particular name, but that name wasn't important, so we get rid of it, and we then conclude something is G. Who is it? Don't know, don't care. We were talking about him as if it was Steve, but that was just a way for us to do it grammatically. The key point here about all of this is that nothing in this reasoning depends on which thing Steve is. Doesn't really matter that we used that name either. We could have used Vladimir, we could have used Stephanie, we could have used any name at all. So not only does it not matter what name we used, but it doesn't matter what object the name stands for. That's the reason why the name is arbitrary. It's just filling a grammatical purpose for us. The reasoning here remains completely general. That's also why we could use this same trick earlier with universal introduction. If the name is arbitrary, then it's literally arbitrary. It could be a name for anyone. So, what you get is this rule. Yes, please. Good.
For X, with X following from the existential, that it means that if everything X is also, G, that something is G by the limit.
Good. So we're still trapped by the grammar of the language. So remember, the grammar of the language tells us we can't just use fx. Fx isn't a sentence. We always have to have, if we're going to treat that as a sentence, x needs to become some name. It cannot just be a variable. So this is why we have to make this circuitous route through arbitrary names. We have to invoke a name to get a sentence, rather than just a formula. It's kind of silly, but it is a restriction that falls from the way we structure the grammar of the language. It's basically like why we need pronouns so often. We need pronouns to perform grammatical functions that we would with normal nouns. But if we just left them off, we wouldn't have proper sentences. That's effectively what we're trying to do here.
Would it be easier to allow the use of variables with the sentence?
It would, but no, then we'd have to go back and change the way that we were thinking about the language we talked about in the first half. So we then have to figure out how it is that we can have a sentence that says fx. What is it asserting?
Oh yeah, that's basically what we need to figure out now, right?
Yeah. So we'd be kind of stuck. Either everything that we kind of said in the first half would become extremely difficult and we need to change the grammar. Or we've got to do this funny thing where we just play a kind of grammatical cheat with an arbitrary name here and then get rid of it. So the nice thing, and this is the important thing, is that whenever we're going to do this sort of reasoning, it's always just satisfying grammatical requirement. We don't lean on it meaning anything. It's a good question, and it's a weird kind of consequence of basically the grammar of the language. It's an kind of fun thing. In Dutch, I'm always kind of weirded out why we have to do is. Like why we need to say that kind of thing sometimes when I really want to just say it's raining or something like that. There's grammatical quirks with every language. This is a byproduct of a very fun grammatical quirk for FOL. So what it means for us in terms of a rule is that we have something like this. And this is the ugliest rule that we're going to learn of the new ones. But it's fairly straightforward. If you have an existential, like we have an n. What you can do is you start a subproof where you've replaced the associated variable, the existentially quantified variable, with some arbitrary name. And in order to ensure it's arbitrary, the name we're introducing can't appear in any undischarged assumption. It can't already occur in the sentence. And the other interesting one is that it needs to be gone by the end. So what we do, we introduce an arbitrary name to start a subproof, kind of substitution instance. We then do some reasoning in our subproof to some conclusion. And this sentence that we're going to get out can be anything you like. But notably, what it cannot have is it cannot feature this name. And the reason is, if it still features that name, then it's no longer arbitrary. It's about that particular name. It has to be gone so that the thing we're concluding could have been done with any name whatsoever. So what you then get is some result that follows from the existential, and you cite the subproof to tell you this is where we did the reasoning using the arbitrary name. And again, the rough and ready thought here is that we're pulling a kind of grammatical fast one. We're going to substitute in place of the existentially quantified variables, some name, but it's not a name for any particular thing. It is an arbitrary bullshit dummy name. We're then doing some reasoning using it. But once we're done reasoning using it, we get rid of it. We don't need it anymore. To go back a slide, that's why we get this last little move, right? We conclude that Steve is a G, but since we don't want the reasoning to be about Steve, about that name, we have to get rid of him. And it's only by doing this kind of move that we end up back making Steve arbitrary, that we could have used Stephanie or Vladimir or whatever name you like. So this is something, the rule will be a little bit easier to kind of get a grip on after you've used it a few times, but the thing to remember is that it's always going to involve a subproof where you start with an arbitrary name and the name you use needs to be gone by the end. So here's an example. This is literally just the natural deduction version of the reasoning I gave a slide ago. We have the existential, there's something that's an F. We have the universal claim for everything. If it's an F, then it's a G. We then start a subproof using some arbitrary name. In this case, I've used A. We can use this name inside our subproof. So we did universal elimination to plug in A in place of X. Note, what that gives us now is a conditional. We have the antecedent, so we can do conditional elimination to get the consequent. And we can't close the subproof here because this is something specifically about the name A. So we have to finish off by getting rid of the name A. And the way we do it is by kicking it out and replacing it with an existentially quantified variable. So our last move in the subproof is existential introduction. And that then allows us to eliminate the existential, that is, derive something from the existential, which turns out to just be another existential. This highlights something that you'll do a lot. Weirdly, most of the time, when you existentially eliminate, you will end up with another existential. Because you always have to, at the end of the subproof, where you're doing your existential elimination, get rid of a name. And the easiest way to get rid of a name is to replace it with an existentially quantified variable. So this kind of last move in the subproof, that'll happen a lot. Okay, now before we go on, pause. What questions do you have for me on these first four? Please. Absolutely. So, in general, what we want to do for existential elimination is we are going to introduce an arbitrary name which replaces all of the existentially quantified variables. We then do some reasoning using it. We get to a conclusion that does not feature that arbitrary name. Because if the name's still there, it's not arbitrary anymore. It's got to be about that name. So what that means in this case, we took our existential in 1. And our subproof is designed to eventually let us do existential elimination. So we start the subproof by replacing the associated variables with some arbitrary name. In this case, any name would be arbitrary, so we just use A. At that point, again, because we want to get ourselves to something that doesn't feature A, we can use the universal here, replace the universally quantified variable with our arbitrary name to get that conditional. That gives us the antecedent and the conditional, so we can derive the consequent using conditional elimination. Now we cannot just conclude the proof and extract GA, because that's about this name. We have to get rid of the name to make sure that our reasoning is entirely arbitrary, that it didn't depend on us using A. So the trick we use to get rid of A and give us a sentence that is not dependent on any particular name is existential introduction. We replace the name with an existentially quantified variable. That gives us this sentence, and this sentence doesn't feature the arbitrary name we started with. So we can now extract it using existential elimination. And the reasoning, again, is that as long as this sentence doesn't feature this name, we could have done it with B, we could have done it with C or E or F or any name you want. But if A was still in there, then it only would work with that name. So it's not arbitrary anymore. So, again, the 3 requirements for existential elimination. Go back. The substitution name that you're plugging in needs to be arbitrary, so it can't appear in any undischarged assumption up to that point. It can't already be in your sentence, and it needs to be gone by the end. Those are the 3. And this is the most ridiculous rule by far, right? The other ones are a lot easier. This is the hardest one. And it's only hard because of the restrictions on what names you're allowed to use. The easiest way to go, to just kind of give you a mnemonic, is whenever you do the substitution, it's got to be a completely new name, one that you haven't seen before, and it needs to be gone by the end. That's the big thing. So one that isn't already there in your proof, and then that you can get rid of at the end. And as a little tip, again, having done this a bunch, a weird thing is that frequently, in order to ensure that it's gone by the end, your last move in the subproof will be introducing an existential. That feels really strange, because you're eliminating an existential to get another existential. But remember, elimination rules are badly named. They're really exploitation or use rules. We're just using sentence one. Okay. Any other questions before we go on? Please. Yeah, sorry. I didn't see you for the pillar.
So line 7, why is that an elimination extraction? Because we still have the not elimination extraction, sorry, existential elimination, because we still have the existential.
Good. So it's again, don't think about this as elimination, just think about it as exploitation or use. And what it's doing is it's using sentence one. So in that sense, it's eliminating the existential, but it's eliminating the existential in line 1. Now what it's giving us, as it turns out, is a sentence that's also an existential. But it's telling us that this sentence follows from this one.
And it's kind of like narrow.
Yeah, in a way. So again, it's don't be misled by the name. Elimination's a bad name. It's really more of use. So it's using the existential in 1, and this is the kind of showing you the subproof where we did the reasoning to say, hey, using this arbitrary name, filling in for 1, you can get this result. So that's the important thing. That was good. Okay. We feel okay with these first 4. Again, don't stress if it's not making sense, because this is the sort of thing, as with so many of these, they'll start to make more sense as we start to do some examples. Just hearing the rule right off the bat is not going to necessarily be very helpful. Okay. So, thankfully, there's not very many other rules left. There's quantifier conversion rules, and there's introduction and elimination for identity. So let's do the quantifier conversion ones very quickly. The CQ rules basically tell us if you have a quantifier next to a negation, you can swap places as long as you also swap which quantifier it is. So if you have universal negation, you can turn it into negated existential. If you have existential negation, you can turn it into negation universal, and vice versa. Again, if you have a negation next to a quantifier, you can swap these as long as you also switch which quantifier it is. This is stuff that kind of makes sense if you think about it, right? So for example, if not everything is A, then at least one thing isn't A. If something isn't A, well, not everything's an A. Or, right, if everything's not A, then there's not going to be something in the domain that satisfies A. Again, the kind of intuitive thought here is hopefully clear, but more importantly, just thinking about it purely in terms of the rules, quantifier next to negation, you can play swapsies if you want, as long as you flip the quantifier. The other thing to note, this is really annoying, and I don't know why Tim did this, so fuck you, Tim, for doing this, right? Is we call them the quantifier conversion rules, but they're called the CQ rules when we write them down instead of QC. It would make so much more sense the other way, but whatever. So, okay. That one's fairly straightforward. And this is useful, particularly going to be useful when we're trying to do things like showing some sentences are jointly contrary, because you can change where negations appear to generate a sentence and its negation, for example. Something useful. So the last two rules have to do with identity. The first one is another very favorite one of mine. Identity introduction. Identity introduction says you can introduce an identity whenever you want. Notably though, it's an identity that has the same name on both sides. So you can introduce from nothing A equals A, or C equals C, or F equals F, whatever you want. This is also the only rule that doesn't cite any lines. You literally just bootstrap a sentence from nothing. It's helpful to note, right? I've said a couple times in the tutorials and things, when we're proving theorems, 99.9% of the time, when you're proving a theorem, your first move is to open a subproof. The very tiny range of exceptions are because you do this first. Because this is the only rule that lets you literally get something from nothing at all. So identity introduction, you can introduce an identity with the same name on both sides. And our final rule, identity elimination. Ooh, sorry about the echo. Yes, please. So one of the things you can do with this is you can get something like, say, introduce this and then immediately do existential introduction. So you could get, there's something that's identical to C. Or you could even get existential introduction twice and get, there's some X that's identical to some Y. And then you might be able to use that for various things. It's very situational. Right? Because again, the only kind of sentence this is going to give you is an identity claim with the same name on both sides. So it's not really going to do much. But it's like reiteration. There's times when it's really handy to have. So, our last rule, identity elimination. Identity elimination is just substitution. If you know that two names are identical, that is, you have an identity with two names on either, like A and B on either side, then you can substitute. If you have a sentence featuring the name A, you can cite the identity in the sentence and substitute some or all of the occurring versions of the names. So you could say, like, if this has like RBB as the sentence, you can then cite like A equals B and get RAB, or RBA, or RAA, whatever you like. Again, if you have an identity claim and a sentence featuring a name, you can substitute the other name for some or all of the occurrences of the name. Nothing really shocking. If you know something about one thing under a name, you also know it for the same object with a different name. Okay. That's it. Those are all the rules. Everything that we've learned already still works. It's just this stuff on top. And all of this stuff on top is really just about manipulating the quantifiers or playing around with identity. So we're at 126. I've got about 20 more minutes of material left. So here's my suggestion. So we just push through and then aim to end when we end. Is that okay with everybody instead of a break? Beautiful. And then we're all already at the train station. We can all go where we need to go. So, cool. Those are the rules. And again, the big thing with all of these is we're going to practice a bunch. We're going to spend the next basically 3 weeks just doing FOL, natural deduction, kind of working through and getting ourselves to a point where we feel comfortable with it. But what I want to do for the last little bit here is I want to talk to you about some proof theoretic concepts. This is going to be very quick because this is going to be very, very familiar. We can say, hey, an FOL sentence is a theorem if and only if there's a proof of that sentence from nothing at all. That is, we take the sentence and we derive it from no assumptions whatsoever. So the stuff that we could do before with TFL, right? We take nothing and then we get down to the sentence. We can do the same with FOL. So we can show that FOL sentences are theorems. You can guess what the next thing is going to be, right? Two sentences are provably equivalent in FOL, if and only if you can take one and prove the other and then take the other and prove the one, right? Construct two proofs, one starting with the left hand and deriving the right, one starting with the right and deriving the left. So this is the same concepts as with TFL. And finally, 3 guesses what the last one is, right? It's the last proof theoretic property. We can do the same here, right? We can show that some FOL sentences are jointly contrary if and only if we can take them as assumptions and derive a contradiction. Again, these are identical to what we did with TFL. So this is very handy, right? All of the same stuff, the same kinds of questions we could do with TFL, we can also do with regards to FOL, which makes sense. It's basically the same system, just with a few extra rules. That's why I said this isn't really super long. But suppose you wanted to show that an FOL sentence is not a theorem, or that 2 FOL sentences are not provably equivalent, or that some FOL sentences are not jointly contrary. It's important to note that we couldn't do this within our natural reduction system. The system just cannot show you these things. Because the system can only produce proofs. It can't talk to you about the various possible proofs you might construct. But we have a tool that lets us do this. And again, I've mentioned this a few times, but I just wanted to drive it home. This takes us to the last section. The proof theoretic and semantic concepts. Now, as you remember from last week, I think it was, we talked about how the single turnstile and the double turnstile match up. They're different notions. The single turnstile means there's some proof that starts with the stuff on the left and ends with the sentence on the right. The double turnstile means either that there's no valuation, if we're thinking of TFL, but what was it in FOL? What was the magic word in FOL? Interpretations, right? So but remember, when we were doing interpretations, we could not show that an argument was valid. All we could do was show that arguments were invalid, or that sentences were not equivalent, or that a sentence was not a theorem, in this case, not a logical truth, and not a contradiction. Well, here's the nice thing. Because these two match up, because they extensionally agree, we have tools now. We can say the argument's valid if and only if the conclusion can be proven from the premises. And if it's invalid, if the argument's invalid, what will we be able to do? What can we do with an FOL argument that we know is invalid? Get it on the midterm. Think about the last question. We can construct an interpretation that makes the premises true and the conclusion false. So, given any FOL argument, we now, if it's valid, can show it is by constructing a proof, or if it's invalid, we can show it by constructing an interpretation that makes the premises all true and the conclusion false. Similarly, if 2 sentences are logically equivalent, that's going to be because they're provably equivalent. And if they're not logically equivalent, what can we do? If 2 FOL sentences are not logically equivalent, what must we be able to do? Again, we did it on the midterm. We can give one interpretation that makes one of them true and one of them false. Yeah, we did this, right? Similarly, if some sentences are jointly consistent, then they are not jointly contrary. So remember, on the midterm, I also gave you some sentences, asked you to show me that they're jointly consistent. And you did it by giving me an interpretation that makes them all true. Well, to show that they're not consistent, what we would do is we take them as interpretation, or take them as assumptions, and derive a contradiction. Basically, our two systems are matching up. Whenever one works, the other fails, and vice versa. you get this beautiful, beautiful alignment. We can think about things in terms of interpretations or proofs, depending on which is more convenient. So if some sentence, some FOL sentence is a logical truth, we can show it by constructing a proof. If it's not, we can construct an interpretation where it's false. If a sentence is a contradiction, we can show it via a proof. How would we show that a single sentence is a contradiction? What would we do? Yeah. We can construct a proof, take it as an assumption, and derive a contradiction from it. Show that it is jointly contrary just by itself. And if it's not a contradiction, then we can give an interpretation where it's true. Two sentences, two FOL sentences, if they are equivalent, they must be provably equivalent. We'll be able to construct the two proofs from A to B and from B to A. If they're not, then we can construct an interpretation that makes one true and the other false. If they're jointly consistent, then we can construct an interpretation where they're true. If they're not, we can show they're jointly contrary with our proof system. And the big one, this is the big, big one. If the argument's valid, we can construct a proof. If it's invalid, we can always construct an interpretation. So wherever one of our tools lets us down, the other one steps in. That's a beautiful, beautiful thing. It's almost like the two systems were designed to match up perfectly with each other. Shocking. But this is a big payout, right? Because up until this point, we didn't really have a way to fill in a bunch of these gaps. If you remember when we finished off at lecture 6, thinking about FOL, there was a bunch of stuff we just couldn't do. All of those instances were just empty spaces. Now that we have our FOL natural deduction system, we have a tool to be able to do those. So no matter what we're presented with, we can now show it. That's handy. That's handy. Now, it is worth noting, you have to kind of take my word for it, that the single and double turnstiles extensionally agree. Showing that they do is actually a very difficult but interesting project. It's showing the soundness and completeness of our systems relative to each other. If you're interested in this, feel free to look over the Meta Logic book that's in the kind of files for our Canvas page. Not really going to talk about it. It's something worth reading if you're interested in these kind of formal systems here. It walks through the soundness and completeness proofs for our two TFL systems. And it's notable that going through those is difficult enough, but there's clear ways to kind of extend this reasoning to cover almost all of our FOL stuff. It's very difficult to show how the FOL systems work back and forwards, but they are going to be sound. They're going to be sound and complete relative to each other. So that's the big kind of payoff from thinking about natural deduction. We did all of the work for TFL, partially because it's very interesting. And again, to give us some insight into how it is that we can go from premises to conclusion, things like this. But the big payoff was to get to this, so that now we can do natural deduction for FOL, and we have a full logical system. No matter what kind of argument we're presented with, we can either show that it's valid or that it's invalid using the tools we've covered. Now, it's worth noting, I am not going to ask you to construct interpretations again. Right? That's the stuff we did in the first half. Those are over and done. So, no stress. But I am going to ask you to obviously do all the ones with a natural deduction, because that's the sort of stuff we've been working on, we've been talking about. So what we're going to do in the next few weeks is, again, work through a bunch of FOL natural deduction proofs to get better, get more familiar with this system, to get kind of conversant with it. So in particular, what we're going to do next week, as I mentioned at the top, next week there isn't going to be a lecture. Instead, what I'm going to do, I'll record a little video with me working through some natural deduction proofs for FOL. I'll post that on the weekend, so either Saturday or Sunday. Take some time to read over that. Feel free, if you have questions, to either email me or post in the kind of forums on the Canvas page. We're still going to have tutorial this week, and we'll have tutorial next week. Because again, the real big thing now is just to get better and better and better at using this sort of system. In 2 weeks' time, we will have another lecture. It will be the last lecture with any new content. And in fact, it's going to have 2 parts. The first part is going to have some content. The second part is going to be entirely supplementary to talk about alternative logical systems. So it's not even going to be full. But importantly, take care of yourselves, guys. We'll hopefully see you all in your tutorials later this week.